Alright, hit the button. Draft physics video. Couple of subjects, just stuff I'm thinking about. Very draft, I guess, in that sense. So somehow I ended up on the subject of magnetism again, and watching something somewhere sparked a curiosity. I guess it's related to the two-slit experiment in light, in the sense that I believe the diffraction is being caused by a field. I guess that's it too. Somebody posted links to this, quantum field theory, which is nothing. I don't even understand why they think it's a theory. It's a theory where they just said gravity is blue and magnetism is red and electricity is, I mean, they just, I don't know, Dr. Seussed reality into nothing. I mean, it doesn't say anything about how, I mean, if you turn photons and electrons into forces, how you've fixed any conceptual problems. So anyway, I'll do the magnetism part first and migrate however it migrates. So I was thinking about current in wires, and it occurred to me the Newton thing. Okay, these electrons are moving, or at minimum they're exchanging this movement of something. Something's moving, and it's moving outside the conductor. It doesn't move inside, it moves outside. That's where the current is. And this induces a magnetic field. And I was thinking that this is sort of Newton's opposite reaction thing. So when you think about electricity or the movement of electrons, there's no obvious equal but opposite reaction. And the equal and opposite reaction is actually coming out. It's not an opposite reaction, it's a lateral reaction. And that's something like how gravity also reacts. You don't see the same kind of equal but opposite reaction because it's the force itself. It's more direct than the things possessing some force interacting with each other. How to put that? There's a difference between acceleration and velocity. There's a difference between the things possessing a imbalance interacting with each other and things acquiring imbalance. So you could argue that in a conductor, that's where electricity is being conveyed across it, that's like acceleration, or that's like the creation of imbalance. Imbalance is being forced. It's not a native property. So, but this gets back to the whole thing of what is magnetism. I don't know if I want to bother trying to do this through pictures or not. I mean, it's a little bit helpful. So here's a conductor, and here the magnetic field is described around the conductor. But this field just kind of represents this middle part of the magnet. And field lines are deceptive because they imply something, but you have to understand what they are. They're artificial. They're what happens when things that are magnetic line up with the force. So although it appears as if the force is doing this thing, it's really not. The force is radiating out, and the what you see as field lines are representations of where the force, what's coming from one side and going from the other side, where they balance, in the sense that these field lines, what they represent is that the force that would be, if you took something neutral and put it right on that spot, it would leave parallel to that spot, implying an equality in the force. You'd have to create a 90 degree off of this, you'd have to have a 40 degree here and a 60 degree here kind of thing, or something like that, implying that. But that's really what's happening, is that although this looks like this is the active part of the magnet, this is really the active part of the magnet. Alright, so how to explain this? Okay, so in a conductor, what I was theorizing is, so just pretend this is a conductor, and as the electricity travels through or across it, what's happening is that it's interacting, it's this whole directional arrow thing. So I guess I'll attempt to draw it. So you have a bunch of what would be represented as directional arrows that you could say that's what the current is. The current is a bunch of this quanta is moving from here to there. Electrons can't move by themselves. Something has to compel them to move. The quanta has to compel them to move. So there's a bunch of quanta in the form of electrons. It doesn't really matter. But there's this imbalance of quanta, which means more arrows are going this way than are going this way. And therefore you have movement. So movement is just a representation of having more arrows going one way inside the thing than going the other way. So you have this imbalance of arrows moving in a direction. And what these arrows are doing to exist is they are interacting, but what they're doing is basically in the substance itself, the material, which let's say is just arrows in many different directions, or the native condition. They're taking the ones that are going this way, arrows that you might possess that are going horizontal to this movement, and those are the ones being released. So for these to go through, something has to come out. So what goes in, something goes out, and the going out part are these horizontal element. And this is true for anything that's acquired velocity, or acquiring velocity, let's say, is that it will be expelling as it's changing its orientation, as it's replacing arrows going this way with arrows going this way, or let's say down for gravity. It's replacing arrows going this way with arrows going this way. So it's changing its matter, its mass, and percentage-wise into more arrows going this way than arrows going this way. And that's why, so it's expelling more arrows out its sides. Now the trick is, I think in conductors, what's creating magnetism, is that some of them fly freely. So that's polarization A, let's say. They are horizontal, and they go out into the surrounding atmosphere. And some end up being the horizontals going this way through the conductor. And so the ones that end up going back through the conductor are the ones that end up with polarization B. And that's the real plus and minus, the positive negative, in the sense that that's creating because you can see that the different angles would be the different, representations of that. But that's the directionality difference, or the thing that causes the distinction, is the ones that leave unmolested, and the ones that go back through the material create a different polarization. So I think that's the nature of creating the difference in the polarization. Is half of the you can call them reflected, but exchanged directional arrows end up going that way. So that's what's happening with these electrons. These electrons are basically conveying to each other directional imbalances. It's not happening to the entire substance of the conductor, it's just happening to the electrons on the surface that are directionally imbalanced. So the surface is moving, but the substance isn't. Yeah, okay. Is there anything? It's a little complicated, but again, the real trick of this is to understand that these filings are all little mini magnets, and they're really lining up. First off, they want to be attracted, but they have friction, so they can't be pulled in. But more importantly is as they line up, they become magnets themselves, and they have the positive and negative poles that force other things to line up with those positive and negative poles. And so these magnets end up repelling each other, and that's why you end up with this spacing, is because ends up being the repulsion between the alignments of the magnets. It's not really representing something that's really there. It's only there to things that are magnetic. And what's the real force is coming out as straight line gravitons or magnetons or whatever you want to call them. Doesn't really matter. But the real force is coming out in straight line vectors, is radiating out. And we're always radiating out because we're in a field that's constantly bombarding us. But again, the pressure is equal. And the only thing we notice is when pressure becomes unequal, when there's more stuff moving in one direction than moving in the other direction. And I guess that could be described as what's happening in a conductor. Now, there was another part of magnetism okay, this image, I don't know if this is accurate. So they describe this field in the conductor as having a momentum of some kind. And I don't think it does. Because I think if it did have a momentum, then you wouldn't have to use alternating current to induce magnetism to convey electricity from one coil to another coil. For a transformer to work, you have to keep collapsing this field and creating the field, and collapsing the field and creating the field. And if the field was moving, you wouldn't need to do that, because it would already have some kind of energy in it. So I don't think this field is moving, but whatever, I don't know if that's terribly important. Okay. So, so magnetism just represents a portion of gravity. You know, the portion of what's being expelled when you're in a gravitational circumstance. Like, see, our gravity is pushing us down, but we're also being pushed back up again. So we don't gain any velocity. So even though we're being accelerated, we have no velocity, because whatever arrows we gain by being accelerated, we lose them again because we're having arrows pushed back into us. So our balance remains equal. So we're not expelling a bunch of extra because the two forces are balancing each other's out. You know, to a net nothing. And that just ends up being again, we can't detect space. Space has all this force in it, and yet we can't detect any of that force. So that's what we're not detecting, is the same force that's in space already. Everything's already moving. All this stuff has energy in it. We only recognize the energy when it's in specific forms. So there was something else I want to talk about. Oh yeah, so I watched a video on, and it was kind of disappointing. You know, do magnets work in space? And so there was this little clip, and then there was this other video related to it that I hit that was more interesting. Well, it wasn't very good. I mean, these documentaries on magnetism are really kind of childish. You know, it's just showing you magnets lifting up cars, and you know, magnets in your phone, or you know, it's all this commercial magnetism. It isn't any explanation of magnetism, which is sort of irritating. So where do I want to go here? So anyway, yeah, the video in space was sort of annoying because they described the astronauts in space as being in no gravity, less gravity, you know, substantially less gravity. And that's not what they are. It's a common mistake, because they think because they're weightless they have no gravity, and it's not that they've avoided gravity. Avoided's the wrong word. It's that they're free falling. They're doing what we can't do because we don't have a sufficient velocity. But if I shoot you into space at the in that way, with sufficient velocity, you'll become free fall. You'll become weightless to gravity if you have sufficient velocity to keep compensating for your free fall by missing the Earth, doing the Elysian thing of an orbit. So the gravity's still there. It's just that your sideways motion is negating the distance you're falling. So you just don't notice that you're actually free falling, which you're actually doing. So you don't feel gravity when you're actually falling in it. When you're actually accelerating, you don't feel the gravity. So, how to say this? So velocity negates velocity in one direction negates velocity in another direction. Well, negates the wrong word. No, never mind that. Pretend I didn't say that. But anyway, it's all about these directional arrows and what your net directional arrows will end up being. And that's what's happening when you're orbiting, is that the atoms are being probabilistically, through occurrence of pressure, will end up, you'll start here and you'll end up here instead of here, because there is this imbalance, and that creates your circular orbit. But it's an optical illusion. You're not really circularly orbiting. That's not how your atoms are getting there. But anyway, that's another subject. Okay, where do I want to go now? So I think that's it. But yeah, I think it's an important, it's a fascinating part of this whole electricity thing, is the way it travels on the outside of conductors, and the way you can induce it. Like there's those experiments with the big ball that gets the big charge of electricity, and the sparks fly off of it, and it's charged, by just throwing charge on the inside, and that creates the charge on the outside. And it's how to explain that? Yeah, but the whole idea of that you can have a very well, I don't know if I want to get into voltages and all that kind of stuff. I was trying to think of a way of saying that the voltage, the stuff really wants to leave. I mean, it's arrows and they want to go. Let's see, how do I say that? But they need a path, and that's what sparks become. Yeah, I knew there was something else I wanted to add about that, but I just can't remember what it was. But it's just a very interesting part of electricity, is that it has this inside-outside kind of function. All right, so let's go to the diffraction thing. So what I was thinking about diffraction, with slits, with surfaces, is that what's really happening is I'm thinking the corners are the key element. So it wouldn't matter how thick something is, it just matters that it has a corner. It has two corners. You can't make a slit without it having two corners. some sort of, it has to have some sort of thickness. It's impossible to have it no thickness. And the corners, so the corner of a slit would have these little peak points at the two corners. So they're the highest point. So they're the point furthest into what would be considered the beam of light. So the beam of light's coming this way. These are the 2 points that are highest on the, as a manifestation of the matter. The matter's furthest influence is at these 2 corners. And what's happening is that diffraction is just a kind of reflection, in that the light is being diffracted by the first corner into an angle that creates a new angle of incidence that creates a new angle of refraction. So it's really just a communication between the 2 corner points. So it's basically 2 reflections that's creating diffraction. And I could theorize that how thick the material would be would make a difference about what would be possible angles of reflection. So it would be interesting to see the 2 slit done with maybe a material that was a 1/4 inch thick or a 1/2 inch thick, and see how different the results are. But it has to do with this coherent light thing. So if I also blow up just this idea of a field of electrons around the surface, and say some light was coming in, this coherent light would be coming in straight. It could theoretically have a 0 or less angle of reflection or refraction, or incidence, an angle of incidence that could be 0 or a negative number, theoretically, where it could be hitting electrons on the other side, the side in between it and the surface, and that could cause dramatic reflection, because you have gone full cycle kind of a thing. It'll do the horizontal thing. So now what goes in comes out at a 90-degree angle to that angle of incidence. So that's what I'm getting at. When this first thing is reflected, the second thing is going to reflect it out at a 90-degree angle, because you've changed the angle of incidence, and that you've gone negative. And so you end up with a highly positive reflection angle. It's like if you put it in at 0, perfectly straight, theoretically it would leave at 90 degrees. So this again is just this exchange thing that I've been talking about taking place, is that you're basically just exchanging these arrows in the end. And light does that also. Light is gravity. Light is this quantum energy. I have to come up with some better language to describe this stuff. Everything is this, though. The balance of everything is decided by the possession of arrows in a direction. And again, any imbalance in that possession will be manifest as something visible, like movement or heat or something that indicates things are moving, because there's more arrows going one way than going the opposite way. And that's all that's being exchanged in all these energy transfers, is just the number of arrows going in a direction. Alright, that might be enough for now. The nature of polarization is still something I haven't quite figured out. Just the fact that it exists. Again, we know it exists with light, and gravity is just a form of light, and so light's just a form of gravity. Sorry. And so the gravity itself could be polarized, and when you polarize the gravity itself, that's what we see as magnetism. And electricity is movement manifested. Not the right way to say it. electricity is a reciprocal to magnetism, in that because of this idea that it flows on the outside of the conductor, that it creates polarization of gravity. See, when I say gravity, that can be misleading, because we think of gravity as being associated with the objects, and the objects are really blocking gravity. The Earth is creating less gravity, in a sense, by blocking it, by absorbing it, by moving, by taking arrows that were going somewhere and essentially possessing them. And what has to be understood is gravity, the real gravity, is out there. It's out in space. It's everywhere. Everywhere has the gravity. And the thing is only reacting to the gravity. It doesn't make the gravity, it reveals the gravity. Maybe that's the way to say it. The Earth is just revealing gravity. The Sun is just revealing gravity. It's not making gravity. It's making an imbalance by moving. Alright. Maybe that's the way to say it. It's absorbing arrows in a direction, and by absorbing arrows in one direction, it has to release arrows in some other direction. That's Newton's equal but opposite. But the point is, it doesn't have to be opposite. It's just tangential. So there's a equal but tangential reaction. And so the equal but tangential reaction to electricity flowing in a conductor is magnetism. Yeah. Okay. I believe that's enough. So yeah, see, there's just such a, it's very simple, I think, in the core. Like I said, it's just this checkerboard with stuff, with simple rules about interkinetic interaction. But what makes it complicated is the fact that these little bits are complex to create these orbits. And then deciphering, doing the addition. See, I need a computer model is what I need. I need a computer to just model the creation of these orbitals, entities. And then, just model the transfers of these arrows, because that's all that's being done. Like I said, an electron does not move because the electron says, I'm going to move. It moves because it acquires arrows, imbalancing arrows, that oblige it to roll because of the arrows it possesses. And it can't possess those arrows without exchanging them with some other arrow, without releasing an arrow in some tangential direction. Okay, that's probably the way to say it. Maybe. Anyway, till next time.